Welcome to this video in the Covalent Bonding chapter. This is 7.1, where today we are going to start talking about covalent bonding. We're going to introduce the concept of covalent bonding and demonstrate how to draw Lewis dot models for covalent compounds, which is going to be significantly different than the Lewis dot models that we drew for ionic compounds. If you have not already done so, please make sure you have your chemistry notebook handy. You got your companion worksheet downloaded and printed out. You have a writing utensil, and of course, we are going to need our periodic table because we are going to be specifically looking at valence electrons. We got a lot to do today, so without any further ado, let's get cooking. A covalent bond is going to be formed when two non-metallic atoms of similar high electronegativity are going to share their valence electrons. And you guys are going to see that the formation of a covalent bond is going to be fundamentally different than ionic bonding, where we saw electrons being completely transferred from a metal to a nonmetal. Well, in this case, we are dealing with two nonmetals which will now overlap their orbitals, and you can see that sort of happening in the animation to the right. Now, why will they share the electron and not transfer? Well, a lot of that goes back to electronegativity, which you guys know is the relative ability to attract electrons in a chemical bond. Now, because we are dealing in covalent bonding with just nonmetals, you guys know those nonmetals have the highest electronegativity on the periodic table. So if those values are close to one another, one of those atoms is not going to want to just lose that electron and give it to another atom. In this case, they are going to compromise. Yeah, we're going to treat them a little bit like people, and they are going to decide to share so they can both have electrons. And that brings us to why two atoms would want to covalently bond. And that is so they can have their 8 valence electrons, which you guys know is the octet rule. And that was covered pretty much in depth in the periodic table chapter and the ionic bonding chapter. So 8 electrons is what every atom is going to strive to have. And we are going to get there in this video by forming covalent bonds. Now, what does a covalent bond look like? Well, those shared electrons in the covalent bond are going to be represented by either 2 dots between atoms, and you'll notice that these dots go in the same places that they did in your Lewis dot model. So here I see these 2 dots that are right there. That represents a covalent bond between the hydrogen and the carbon. And we see there are 4 covalent bonds that are here. You can also represent the covalent bond by the dashed line. This is really the go-to for how to represent covalent bonding and is much quicker and easier than the 2 dots. So at the end of the day, after 2 atoms have covalently bonded and now shared electrons, the end result is the creation of a molecule. And so that is why sometimes covalent bonding can be called molecular bonding. So you may hear it referred to interchangeably. They mean the same thing. Let's now dive into drawing Lewis dot models for covalent compounds. You guys are going to need your companion worksheet, you're going to need a pencil, and you are going to need your periodic table. If we look at the top of our companion worksheet, you're going to see that there are 5 steps to drawing a Lewis dot model of a covalent compound. If you don't have your companion worksheet, make sure you copy these down in your notes. And once you're done, let's move on and try an example. So the first dot model we are going to draw is that of carbon tetrabromide. So the first thing we got to do is say, well, what is the formula of carbon tetrabromide? Well, I remember my nomenclature, and I know that is 1C, and tetra means 4. There are 4 bromines. So CBr4 is carbon tetrabromide. Step 1 on my companion worksheet says add up all the valence electrons that are in carbon tetrabromide. Well, I know I have 1 carbon and 4 bromines, so I got to go to the periodic table and see how many valence electrons each has. And if I do my simple math, I have 32 electrons in my electron bank. Now, one of the cool things about covalent bonding is you have to use all of those electrons to create your Lewis dot model. You cannot use more and you cannot use less. 32 is the number of electrons that will be present in your dot model, or it is incorrectly drawn. So now we move to step 2. Step 2, after adding up our valence electrons, is draw the skeletal structure. That is the bare bones of the molecule with an element in the middle and then the other atoms all around the outside of it. Now, the way that we have to figure out who's in the middle is pretty simple. The least electronegative atom goes in the middle. So I could very well go to table S and look up the electronegativities, but I also know about another rule for who goes in the middle, and that is called the H rule. The H rule says that halogens and hydrogens never go in the middle. So make sure you take that down into your notes. So in this case, we have carbon bonded to a halogen from group 17 here. So I am not putting bromine in the middle, which means I am putting carbon in the middle. And at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock, I am adding my bromine atoms into my dot model. That brings us to step 3. I had 32 electrons I have to use. You know we got to use all of them. I am now going to subtract 8 for the shared pairs of electrons that I put into my skeleton. That leaves me 24 electrons left. So now that brings me up to step 4, which says place the remaining electrons around the outer atoms first, a pair at a time. Once all the electron domains around the outer atoms are filled, now you can move to the inner atom. And in this case, we never will move to the inner atom because our carbon on the inside already has 8 electrons. So let's see if we can use up all 24 electrons. We're going to do it a pair at a time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24 finishes my electrons from the electron bank, leaving me no electrons. So now what I got to do is figure out, have I satisfied the octet rule for this molecule? And I'm just going to change my color here so to make it a little easier to see. I'm going to count my electrons up, because if I haven't achieved 8 electrons in the valence shell, I'm going to move to step 5, which is the Robin Hood rule, which we will get to in a second. So let's start in the middle. Does my middle atom have 8 electrons? Well, I've got 2, 4, 6, 8. That's a full octet. My carbon is good to go. Now let's look at the bromines. This bromine has a shared pair of electrons and 3 lone pairs for a total of 4 pairs of electrons. 4 times 2 is 8. He's good looking. This guy has 2, 4, 6, 8. He looks good. 2, 4, 6, 8. He looks good. 2, 4, 6, 8. He looks good. And lo and behold, I have a completed Lewis dot model for carbon tetrabromide. You'll see here I circled my 8 electrons on each, showing in a Venn diagram of sorts where the electron is overlapping and shared between the two of these. You do not have to circle it. It's just me showing you that we have achieved the octet rule and things are hunky-dory in molecule land. All right, let's get in here and try another one of these. Here we have nitrogen trifluoride, and I have given you the formula. So let's go right to step 1. Let's total up the total number of valence electrons we have to use in this molecule. We're starting with nitrogen, which has 5 valence electrons, and we have fluorine. We have 3 of those, and each one has 7 valence electrons for a total of 21. Let's get our sum. That gives me 26 electrons that I have to use in my bank. Now, the next thing I got to do is figure out the skeletal structure here. Who goes in the middle? Well, we know it is the least electronegative. So if we go to table S and we look up the electronegativity values, we get 3.0 for this and we get 4.0 for that. But wait a minute. We also know that hydrogens and halogens never go in the middle, and fluorine is a halogen. So we are going to draw our skeleton with nitrogen in the middle, and we are going to place a fluorine on 3 sides of it at 12 o'clock, 3 o'clock, and 9 o'clock. Step 3 says subtract your electrons from your total that you used in your skeleton. I have 3 shared pairs for a total of 6 electrons. That's going to leave me with 20 electrons to now use for the rest of this molecule. So step 4 says place remaining electrons around the outer atoms first, a pair at a time, then put any leftovers on the inners. We're going to start here. We're going to go a pair at a time. 2, 4, 6, 8, 10, 12, 14, 16, 18, 18 on the outer atoms. That leaves me 2 electrons. I can't put any more here on the outer atoms. So where do I go? Well, that's right. Got to go to the inner. My nitrogen already has 6 electrons, but it could use 2 more. We're going to put a lone pair of electrons on the nitrogen atom. So once I do that, I got no more electrons in my electron bank. Now we got to make sure that we have 8 electrons and have a fulfilled octet for every one of these atoms in the molecule. So now let's start counting. We have 2, 4, 6, 8 here. The fluorine is good. 2, 4, 6, 8 here. The nitrogen is good. 2, 4, 6, 8 here. The fluorine is good. 2, 4, 6, 8 here. The fluorine is good. This is a completed Lewis dot model, and it is looking A-okay. So now it is your turn. Pause the video now and draw the Lewis dot model for water. I'm not going to tell you the formula, but I'm pretty sure you know what it is. So pause the video now and then unpause when you are ready for an answer. Okay, if you drew your water like this, you are incorrect. That's right, water is not a linear looking molecule. In fact, water looks very much like this, with a bent structure. And to understand why, we have to understand something about the oxygen itself. So let's now dive in and talk about the Lewis dot model of an oxygen atom. You guys know there are 6 valence electrons, and when we distribute them, we put 2 electrons in the S, which we see here, and then we put 1 in the P, 1 in the P, 1 in the P, and then double up there. That leaves 2 available open electron domains, which are right here and right here, to go make covalent bonds. So the only place that those hydrogens could indeed bond are at the 9 o'clock and the 6 o'clock positions. So the big takeaway from this slide is water is a bent molecule and is not linear. So please do not draw it as such. You will be that guy and it will be incorrect. Okay, now it is your turn to redeem yourself. Draw the Lewis dot model of an iodine molecule. Pause the video now and then unpause when you got the answer. Okay, if you guys did that one correctly, here is what you should have gotten. Iodine is a pretty simple molecule. We're just going to have 14 valence electrons, and we are going to distribute them like this. It is a linear molecule with only 1 shared pair in the middle, and the rest of your lone pairs or your non-bonding electrons go around the outside of the iodines. All right, let's give this next one a shot. This molecule is called Freon, and it is a chemical that is found in refrigerants. So pause the video now, and then when you think you got an answer, unpause. All right, if you did this one correctly, here's what you should have gotten. Now, there was a lot of atoms that were here, and you were probably trying to figure out who goes in the middle, but alas, a lot of them are hydrogens and halogens, so none of them could go in the middle with the exception of your carbon. So I'll give you guys another hint. Generally, the first element goes in the middle. Now, if you don't remember to put the least electronegative in the middle, or you don't remember that hydrogens and halogens never go, you can take a gamble and put the first element that's there. I would say 80% of the time, the first element is gonna go into the middle. Now, you're probably sitting there at home thinking to yourself, wait a second, we have not used step 5 yet, which is in a case where your central atom winds up with less than 8 electrons, and we have to form a multiple bond. Well, guess what? This next example is going to have you guys have to do that. So let's do this one together, and then we'll set you free to try one on your own. All right, so here we have oxygen gas. So let's draw the Lewis dot model, and we already did a little spoiler. We know we're going to have step 5 happening at the end of this, but let's just see why we have to use step 5 and how to get there. So first thing we do, formula, oxygen gas is O2. Remember, oxygen is diatomic. So knowing that, we know that we have oxygen, there are 2 of them, and each has 6 valence electrons for a total of 12 electrons that I have to use in the Lewis dot model. So there are only 2 atoms here, so we know there's nothing in the center. We are going to flank them next to one another like this, and with 1 shared pair of electron in there, I am going to subtract those 2 electrons, and that's going to give me 10 electrons. So that puts me at just finishing step 3 in my 5-step process. On to step 4, place the remaining electrons around the outer atoms first, a pair at a time, and then the inner. Well, there is no inner, so let's just go put them outside. So here we go. 2, 4, 6, 8, and 10. We have now used our 10 electrons, and that leaves us 0 electrons in the electron bank. So let's now see if everybody has 8 valence electrons. So if I look at the right oxygen, he has 2, 4, 6, 8 for a total of 8 electrons, and that has the octet rule fulfilled. And now the left oxygen is 2, 4, 6. Wait a second, we don't have 8 electrons. So this is where rule number 5 comes in. It says, if the central atom, or any atom in this case, winds up with less than 8 electrons, we are going to form a multiple bond, and we are going to do so by borrowing the electrons from the rich and giving them to the poor, which is what I would like to affectionately term the Robin Hood rule. So who is electron rich? Well, clearly it is the oxygen on the right, where you can see there are 30 lone pairs of electrons. So what we're going to do is we're going to take one of those, and we are going to slide those electrons in to the bond domain between the two oxygens to form, you guessed it, people, that is a double bond. By doing that, we now have this molecule, which is your oxygen on the left, the double bond, and the oxygen on the right. By doing that, everybody now has 8 electrons. This one has 2, 4, 6, 8 for this oxygen, and now on the right, 2, 4, 6, 8, and we have a happy Lewis dot model. Okay, now that we have successfully applied the Robin Hood rule, let's have you guys draw carbon dioxide. So pause the video now, draw the correct Lewis dot model for carbon dioxide, and then unpause the video. All right, if you did this one correctly, this is not what you should have gotten. That's right, folks, this is not the Lewis dot model for carbon dioxide. A lot of people leave their carbon dioxide like this after using all of their 16 electrons, but the truth is, if you look closer, not every atom in here has 8 valence electrons. Yes, the oxygens do, but the carbon does not. So don't be that guy. What you should do if you are going to do this correctly is apply the Robin Hood rule and steal from the rich and give to the poor. We are going to take the electrons from the oxygen, slide them into the bond domain here, create a double bond, and we're going to do that with these lone pairs of electrons too from this oxygen. So we in effect will actually have 2 double bonds that are there, and our Lewis dot model should look like this for carbon dioxide. So don't be that guy. Make sure you follow all the rules and dot your I's and cross your T's, and make sure you check to make sure that everyone has 8 valence electrons. Okay, here is our last problem to have you guys try, and this puts everything together, and if you could do this, you can do any Lewis dot model that we are going to throw at you. So draw the Lewis dot model for nitrogen gas. Pause the video now and then unpause when you think you have an answer. Okay, if you drew this one correctly, here is what you should have gotten. Yes, indeed, this is a strange-looking molecule. You have a triple bond here. We had to apply the Robin Hood rule because we only had 10 electrons to place, and by doing so, neither nitrogen had a full octet. So what we did is we stole from the rich, gave to the poor. We pulled the lone pair of electrons from up here, dropped it into the bond domain. We still didn't have a full octet for this guy, so we dropped his lone pair of electrons into the bond domain and created 3 shared pairs of electrons. So there are theoretically 6 electrons that are sitting in the domain between those nitrogens. And that, my friends, is pretty much it for Lewis dot models. That brings us to our burning questions. Remember, if there's anything that was vexing you, anything that you found difficult, anything that you're wondering about, make sure you bring those questions up in the burning questions segment tomorrow. So that is it for me. It's been a pleasure taking you through LDMs for covalent compounds. I will see you on the flip side. Peace out.
That's all, folks.